Now we have one more applications. This time let's talk about some applications on order property. Here we go. And okay, here are some examples. Prove the following statements. If x is greater than 0, then negative is x is less than 0. Excuse me. If x is greater than 0, then negative x is less than 0. If x is less than 0, then negative x is greater than 0. Holy cow, how do we prove that? By the way we defined the order property was done through inequalities. We did not use the notion of positivity. So in order to establish the positivity, we have to do this. And we cannot use positivity because this is going to be an intermediate step. Alright, how do we prove that? The proof is amazingly simple, to tell the truth. Here we go. If x is greater than 0, we just subtract x from both sides, or more precisely speaking, add the additive inverse of x to both sides of the inequality. And then we get 0 is greater than negative x, because left hand side is x minus x, which is 0. Right hand side is 0 minus x. Same for the second. X is less than 0, we just subtract x from both sides, then we get negative x is greater than 0. Which properties did we use, by the way? No, not that cell. This one. We just used this one. Inequality preserves the addition. Okay, how about the next one? If x is less than y and z is negative, then xz is greater than yz. Yes, if you multiply by a negative number, you have to change the direction of the inequality. We can prove it because we established that if z is negative, then negative z is greater than 0. Negative z is positive. We proved it in part A, so we are in good setting. Here we go. Let's begin with x is less than y, and negative z is positive. Why? It's not really give me kind of thing. We proved it. We spent some time and proved it. And then let's use it here. And then finally, one more thing. X times negative z is negative xz. Y times negative z is negative of yz. Is that true? Actually, yes, we proved it. Where? We proved it here in 3.3a. As a matter of fact, I didn't. I did only the first half and left the second half as a homework. So if you did your homework, you did it. If you didn't do your homework yet, then you didn't do it yet. Assuming the students did the homework or will do the homework, let's use it. X times negative z is equal to negative xz. Y times negative z is equal to negative yz. Now everything is in good place. We can add some numbers. We can add xc plus yz, and this blue xc will cancel this one out, and this red yz will cancel those out, and we get what we want. Okay, final example here. Is that the final example? Let me see. Okay, it's not really a final example. Alright, let's prove this one. 0 is less than 1. This is one of my all-time favorite problems. How in the world are you going to prove that? Well, as a matter of fact, we know that 0 is not equal to 1. As a matter of fact, in the properties of real numbers, in the algebraic properties of real numbers, we assumed that multiplicative identity is not equal to 0. We assumed that. But is it greater than 0? I'm not so sure. We have to prove it. So let's prove it. And how do we prove it? Well, this time let's use a proof by contradiction. Let's suppose let's suppose 1 is less than 0 and go from there. Let's suppose 1 is a negative number and go from there. We know 1 is not equal to 0, okay? So if I cross out the other case, then we'll be through. So let's assume 1 is less than 0, and then we just multiply 1 to both sides of the inequality. Because we are multiplying by a negative number, we have to change the order of inequality. That's what we see over here. And now, what is 1 times 1? That's equal to 1, because 1 is 1 times 1. 1 is the multiplicative identity, excuse me. What is 0 times 1? That's 0. We proved it. We proved it in section 3 here, right here, 3.2a. We proved it. So 1 times 0 is 0. So what we get? We get 1 is greater than 0. Wait a minute. If we assume 1 is less than 0, then we end up with 1 is greater than 0. That's contradiction. Consequently, this is not true. 1 is not less than 0. We know 1 is not equal to 0. Consequently, 1 has to be greater than 0. There can be other proofs, but this one works out. Don't worry, I'm not going to write this kind of problem in the exam. How about some other things? Absolute value. Let me see. I think our textbook author, the second textbook author, defined absolute value like this. Let me check. Yes, according to Spivak, the absolute value was defined like this. And then you can prove that absolute value of x is square root of x squared as a theorem. That's the way the other textbook is working, and we're following Spivak's book this week, so let's use this as a definition. And you can prove the triangle inequality, this one, using, well, the brute force method. And did I put proof? No, I didn't really bother, just too tedious. Consider 4 cases, both positive, both negative, one positive, one negative, one negative, the other positive, kind of like that. And then you can use the triangle inequality to prove something like this. I think I left it as a homework, so you can go ahead and do that. If we apply triangle inequality repeatedly, then you're gonna get something like this. How? Well, here's a naive method. Start from here, and then we can decompose into x1 plus the next bunch, and then use triangle inequality like this. And then use the same thing again to this one, the x2 plus that one is greater, and some further, and then repeat. We're gonna get something like this. It works, but it's a bit too naive. So if you wanna go with a little bit more complete proof using mathematical induction, here it is. You can decompose it first using the first original triangle inequality like this, and this red part is less than or equal to that red part from the inductive hypothesis, because there are n minus 1 numbers there. Consequently, we have what we want, and that is a little bit better proof using mathematical induction. Okay, we have a little bit of time, so let me talk about some terms. A set X is called partially ordered if satisfies this kind of condition: reflexivity, antisymmetry, transitivity. And an example of a partially ordered set is a set inclusion. For example, if we have this kind of set 2, 4, and that set is less than, kind of like this in terms of set inclusion, but the set inclusion is not linear because not all pair of sets can be compared. For example, if you take this one as 1 to 5, for example, then of course this is not true, but also the other direction does not hold either. In plain language, these two sets are not comparable in terms of set inclusion. So ordering is just partial. Those kind of things are called partially ordered set. Linearly ordered or totally ordered, that's kind of like real number system. All the numbers can be put into a line. Set of rational numbers is also linearly ordered, but if you just arrange rational numbers in a certain number line, then there are plenty of gaps called irrational numbers. Well-ordered set satisfied this condition. For every subset there is a minimum. An example of a well-ordered set is a set of natural numbers, because no matter what subset I select, there is the smallest element. For example, if you select an integer, even that is not a well-ordered set, because if you select all the negative integers, then there's no such thing as the smallest negative number. There is the smallest positive integer, 1, but there's no smallest negative integer. Well, that's about it for ordering properties, and that's the conclusion of week 2.